Good afternoon, everyone. I am Franco Saliola. I am the new director of the CRM, and I am delighted to welcome you here to this distinguished lecture series, the second edition of this lecture series in mathematical physics. So this lecture series is made possible through a generous donation from Mrs. Tatiana Patera to the Yuri Patera and Pavel Winternitz Fund, which was established to commemorate the significant contributions of these two CRM members to both the development of mathematical physics here in Montreal and to the CRM itself. So I think most people here are already familiar with the CRM. So I'll just say quickly that the CRM is an internationally recognized research institute in the mathematical sciences, and it was founded almost 60 years ago. It's still going very strong. Its mission is threefold: to support excellence in research in the mathematical sciences, to train our next generation of researchers, and I see a lot of young faces here, which is great, and to promote mathematics to a larger public. Through its flagship thematic programs, as well as the numerous summer schools, scientific meetings, and prestigious lecture series like this one, the CRM welcomes over 2,500 people every year. So it is now my pleasure to invite Lenia to introduce today's distinguished researcher.
Thank you, Franco. I'm pleased to introduce this year's speaker, Boris Feigin, who is my teacher, and my dear friend and collaborator. He now works in Hebrew University of Jerusalem. And before we worked together at the HSC University Moscow for many years. Boris is known for many foundational contributions to, say, for example, to the representation theory of Virasoro algebra, BRST cohomology, for foundation contributions to cyclic cohomology, additive K-theory, geometric lengths, many different things. And what he's going to speak about today is quantum groups, vertex algebras, and geometric invariants. So it has to do with both representation theory, geometry, mathematical physics, and tying this all together.
Okay, so thank you. And what I want to talk about today, it is maybe explain you some new trend or new directions in a relatively old story. And this old story is the following: that we have falling objects. No, all of them actually related with physics, but I'm a mathematician, so I'm talk about all this as a mathematician, but it is tensor of categories and quantum groups. Yes, second things related to this is different field theories, but no, because it is only 1 hour to talk about, I will talk only about conformal field theory. And no, it is well known for a rather long time that these two things are in a great relationship. And third things which invariants of different algebraic geometric objects. I want to talk most traditional and standard invariants of manifolds. and such manifolds usually are three-dimensional or four-dimensional. No, why small dimensions are here? Because of several reasons. From the point of view of such invariants, they're simpler. From other point of view, maybe more complicated. But anyway, this story is starting maybe with Witten is the fact that if we have something like this, then and if we take a three-dimensional manifold or not or braid, but I will talk about three-dimensional manifold, we can find some very interesting invariants of such manifolds. No, which is actually really deep things. And again, from the point of view of physics, it means that we have a three-dimensional manifold, and we can construct some not conformal field theory, actually, but topological field theory related with this M3. And if you are a physicist, you are interested in statistical sum. And this statistical sum, from very rather non-precise way, it means it is continual integral over some set of fields here. And if we manage to calculate, it gives us invariant. Anyway, such so what? No, I plan to do what? I plan to explain or recall people general scheme how such story is working, and it is some kind of generalization, and generalization which I will talk about. It is only part of a story, but if we have three-dimensional manifold with additional structure, and this additional structure is a rather representation of fundamental group to something, to some Lie group, or it is the same as flat connection on a manifold, and for such data, it is also natural to connect invariants, and no, people want to do it, but they're in some sense they're defined, but not fully, and surely not investigated enough. But now to explain you what I'm talking about, let me say a few words about what mathematical structure is here. Then we are talking about some part of three-dimensional topological field theory, and maybe mathematically, at least part of it, it is the following. So we have three-dimensional manifolds, and also we have two-dimensional manifolds, which play their role for them. And no, surely if you have three-dimensional manifold, that two-dimensional manifold, say E, is appear in when you study this as a boundary well And very, very briefly, the structure of the story is following. That if you are talking about such kind of topological things, there are several ingredients. First ingredient is some kind of this scheme, or rather old, and people, maybe a person who first formulated was Graham Siegel many years ago, and he explained the following: that first, suppose E is a Riemann surface, something like this. We are talking about this topologically, it is just a two-dimensional manifold or something like that. And this is some conception which is calling conformal block, because it is from here. Or other name is modular function. What is this? First, it is some way to correspond to Riemann surface, some vector space depending in E. In a good example, to each Riemann surface, I want, I want, and conformal field sphere and all this business corresponds some vector space. This vector space, in good example, it is finite dimensional. Actually, in a little bit more complicated example, but also important not, but in our case it was like that, finite dimensional. And such correspondence, it is sort of gomology or cogomology-like. So it is, no, usual gomology, it is some property. So if you have a manifold, but topological space, E, then we correspond to this space of gomology of E. And such things is natural. So it means that, for example, if you have a group of diffeomorphism E from E to E, or not only diffeomorphism, but diffeomorphism for sure, that it is such diffeomorphism acting here. Yes, and surely if you deform diffeomorphism a little, then the transformation is rigid, so it is depending on topological class of this diffeomorphism. No, so anyway, it means that such kind of construction expected to be natural. So natural object like tensor, where on tensor diffeomorphism are acting, but here it is something like that, even more. It is something like cogomology. But we have more than that. So again, we have E, we correspond weird theory. So the theory can do that. So we have not one modular functor, but in principle many of them. So it is a lot of properties and a lot because of many desires, but some main properties. Suppose we have a Riemann surface. It is not necessarily connected, but suppose for a moment this is it. And suppose that this surface is a boundary. So this is E, this is some manifold, and E is the boundary of this manifold. In this case, if we have such kind of structure, then we want this manifold M determine some vector V inside the modular function. So this is what we want. So well, so what we have now, we have E. It is some vector space which is corresponding to E, and if we have this, it gives us some vector, and in principle, if we have a different manifold, then it has different vectors. So it is one element of a story, and the second relationship with invariants is following that. Let me write it here. So now I skip several details, but a little bit non-precise is the following. So suppose we have surface and we have it is boundary of two things. It is M1 and it is M2. Yes, and so we have two manifold with a boundary. We can glue them and get a manifold three-dimensional without boundary. But if we have such structure, then in V of E is here. We have two vectors. One vector depending in what was my notation for M1, second depending to M2. Yes, and we can try to find scalar product of them. For that, we need surely some kind of scalar product here, or Hermitian form, it depends. Usually it appears with this form. I do not explain details, but anyway, yes, and it is usually better to say that such construction depending in orientation. So this is living actually in V of M, and this is living V of M star. But it is some technical details. Anyway, such kind of scalar product is invariant of three-dimensional manifold. If no, at least we want it, because this is invariant and it has to be a statistical sum of some theory. Yes, and the story of this is long, and a lot of facts people know. Yes, no, for example, if it is really invariant, so it means that it depends on three-dimensional manifold. We can cut it into pieces by many ways, and we want to get the same number. And so it is some kind of important condition. So, this is structure what we want, and I will now to present a new example. It is not so easy to do, maybe I try a little bit later, but I need to formulate first what is going on. So, and maybe I want to mention that it is at least two approaches to that, which are deeply related. One using language of conformal field theory, and second language using the quantum group and tensor category. If this second, such kind of invariants, usually they have name, Reshetikhin-Turaev invariants. And if you use approach from topological theory, it is maybe better to call Witten invariants or something like that. But no, the story that they are not completely the same, but overlap very much. And now, what kind of construction of this modular functor, which going from conformal field theory? No, I have not possibility to explain what is conformal field theory, but it is working by the following way. First, if we do this, then in conformal situation, we are working not with the Riemann surface, but actually with algebraic curve. No, it is surely more than just Riemann surface. It is two-dimensional manifold, but we have also complex structure. Yes, and now in conformal field theory, how it is working, I explain with some example. Suppose we have algebra, Lie algebra SL2. Suppose we have Lie, what is calling Kac-Moody algebra. So what is this? No, SL2, this is Lie algebra of 2 by 2 matrices with trace 0. And this is the following things. This is SL2 times CT inverse. Yes, and actually it is a little bit bigger. We need central extension. But what is this? It is just 2 by 2 matrices, but over the field of Laurent series. Yes, and such kind of algebra, it has nice representation theory, and no, it is just a name right now, but a representation which we are talking usually using. So what is this? It has subalgebra SL2 times C. Yes, and we can take trivial representation of this central element acting by number. We induce to the whole algebra. Yes, this is induced representation. Yes, and usually this notation is for irreducible quotient. Anyway, it is some representation of this algebra depending in this number k, and after that we make up the following construction, this is construction of co-invariants. It is working by the following way. So again, I have curve. Let us fix some point, P. Actually, the result does not depend on it. Yes, and let us parameter T be local parameter in this point. Again, in fact, nothing depending in the choice of this parameter, but for simplicity, let us say this. And we have this algebra SR2 hat, which is acting here, living here. It is living just, let us say that if we have such kind of construction, then what we do, we put, in some sense, this Lie algebra to a point. And if we have a representation, then we can put a representation in a point. So it is, a situation is like that. Anyway, it is nice story. It means that we have curve, and again, if we refer to some physics, it means that to each point we manage to put some space of state. So, and it was really like that. So we have some kind of quantum theory, and it has space of state which is infinite dimensional, and we just put it in a point. And to each point we can put such kind of space, but next element of a story, if we have this, we are trying to anyway, so this space of state knows something that it is living in this point, but this no, because we for this we use this Lie algebra, or we use some local data. It does not know that we are living of a Riemann surface. But if we want to construct some space of state which knows this, we are doing the following also rather standard construction, and this construction is working by the following way, that we have again a point. Here we have SL2 times C inverse. Yes, and also on this Riemann surface we have functions E minus P to C. So they are just galomorphic, no, algebraic maybe if you like, functions from this to C, which has, this is some space of functions, maybe AP denoted, and they have singularities only in P. They have poles there, and they are all regular outside. AP is just ring, so we can take SR2 times AP. So what is this? It is just functions from E minus P to SL3. And if we expand some such function in point P, we have a map from SL2 times AP to this. to this SL2 times C inverse. And no, in mathematics, it is also very standard things appear in we try to deal with automorphic form or something like that, but I need the following, that in a point we have representation, which is V depending in P, and this is representation of this algebra, but this thing is subalgebra, and I can factorize by action of this here. No, had this notation. So this is a representation which is sitting in this point. It is this. So this is a representation of big algebra. Actually, it's projective representation. Central element is acting, but after factorization, we get some vector space which is really dependent in E. Yes, and there are some conditions when this space is finite dimensional. In many cases it is so. Even here we have parameter k, and k, if k is integer, for example, and our space is irreducible quotient, in this case this space is finite dimensional. Yes, and anyway, the logic, I think, is the following, that no, it is just example, but we have a complex manifold. It is one-dimensional. We have point, and this is some algebra which is living in small vicinity of this point. Small puncture vicinity, but it is some algebra, and all of them are similar to this. Vertex operator algebra, if you use this word, it is something like that, some algebra which you can put in a point. And it has a representation, and we can make up the space of co-invariant, or in more complicated case, we are talking about homology of a P with coefficient in this, because sometimes we need higher homology. It is not for today. Yes, and then we make up quotient, or this is the same, dual things are functional from this VP to C, which are invariant with respect to this group. Yes, and logically it is rather natural. It means that we have space of state which are living here, and we find out here some vectors or covectors which are invariant with symmetry group of this curve, and the quotient is very standard construction of modular functor. Anyway, it depends on conformal field theory. And conformal field theory, it is just a way to put something in a small vicinity of a point. So conformal field theory in one side and modular functor in other side. And what about property of construction, which appear in, there are several important points, and such important points are following. That first, we get for each E, vector space VE, no, which surely, because of such kind of construction, depends in choice of complex structure. From the very beginning, maybe, of conformal field theory business, people notice that actually no, again, because if you are talking about physics, so in physics you have manifold, and suppose Riemann metric on this manifold, and not in this case, in non-conformal field theory, what you are doing. You want to find statistical sum and so on, but you determine the space of state. And this space of state depending on Riemann surface, on manifold and Riemann metric. Next element of a story, usually the following. What is happening if you change this Riemann metric a little bit? That in principle, it very much depends on what you are doing, but in this case, it depends not in Riemann metric, but a complex structure. Or this is the same, this is as conformal. Not Riemann, but conformal structure on E. Next element of a story is that suppose we take a complex structure on E and change it a little bit. So the question is how our construction depends on it. And the answer is not much. So if better to say that if we have family of complex structure, and suppose it is some family depending in parameter maybe x, and so it is we can make up for complex structure here and complex structure here, but it is some kind of connection. This is some identification, actually up to a scalar, but what is here and what is here. Yes, and so it means it depends on complex structure, but depending is not so strong. And if for conformal field theory, it looks very natural. If you try to formulate what is it, it has to be. So, and if we have set or maybe manifold of complex structures, then, and if we have such kind of lines there, then this structure gives you some operator acting on V of epsilon. So space of complex structure is usually named is Teichmüller space. No, I forget how to write Teichmüller correctly, so let me not to do it. Yes. Anyway, because of but Teichmüller space, it has some fundamental group, and this fundamental group is calling Teichmüller group. Actually, this is a group of diffeomorphism of Riemann surface factorizing by connected component of 1. So it is group of topologically non-trivial group of symmetry of a curve. And because of this, such kind of symmetry are acting on V of epsilon. Yes, and more than that, the structure which I claim we get, it is some generalization of this. So, well, suppose I have Riemann surface and three-dimensional manifold M. Yes, and such three-dimensional manifold M we want, because I started with this, give us some element here. But it is really so, because how we can think about this? We can take some function here, which is the level of this function, f of 1, this is a function, yes, and from some kind of Morse-like function and so on, and it is a function here to R. Actually, better to say to segment 0, 1, f minus of 1 is just my E, f minus 1 of 0 is just point, and other fibers are something here, maybe bigger genus or smaller genus, does not matter, but from this point of view, M three-dimensional manifold can be understood as some kind of family of Riemann surfaces. Yes, and so it means that fibers of F from here, it is point, if we take near, fiber is S2, and S2 start to evaluate from 0 to 1. So it is going, but after that, in a singular point, it makes some transformation. It becomes, for example, torus. After that, it is going on and maybe become like this. After that, it can become again torus. And in the very end, we end with this boundary. Yes, and modular functor of S2 in good example is just C. And so we have evaluation of this to the surface, and actually something like connection. It gives us a map from what we start with these two, and the end of all this. Anyway, even it is a theorem, surely it is known a long time ago, but it is not very easy to check it, because such to check what? That in a space V of E, we get vector by such a way. It is some transformation. We start from the beginning, go, and end with this, and so all structure which we use, function, but actually a little bit more than that, gives us some vector here. But statement is that this vector depending only in three-dimensional manifold, and even it doesn't depend much in complex structure. So this is how such kind of construction is working, and let me formulate some interesting principle or fact about this story. So we have a Riemann surface E, and we can correspond modular functor. And property of this modular functor, it is something like homology, but it is a rather richer structure. rich in the following sense, that structure on E determine something, in my case, is vector in V. Yes, and such kind of structure can be different. And actually, what is a part of my story, A is first structure. Structure on Riemann surface is just a three-dimensional manifold such that our surface is the boundary. For such data, we correspond vector. B, I did not explain it, and maybe it is not reasonable to give details, but this construction can be different one. And actually it is several choices, but so I started that E. No, for this construction, I need complex structure, but I claim that what we get is topological. So actually, this space does not depend. We can forget about complex structure and just think about pure topology. But we used complex structure. From this point of view, it means that if we fix complex structure, then it gives us also vector in this modular Panther space. So it is also interesting in the sense that if I have this surface that from the first glance of very, very different structures, in some sense lie on the same shelf. So I can do correspond vector either to complex structure or three-dimensional manifold, and both of them give us some vector. For example, it means that I can, if I want to use this for construction invariants, then, as I said, one way is pure topological. It is like this, and I get two vectors and take scalar product, and it gives us a number. Or I can take three-dimensional manifold and complex two things. One vector corresponding to three-dimensional manifold with boundary. And second, this M kind of this M3. And second vector correspond to complex structure. And I can take scalar product, and it gives us also rather interesting invariant. Or I can take two different complex structure on a curve, produce vectors, and calculate scalar product. It gives us invariant of two complex structure. Or I can, if to go to more standard things, I can take complex structure and dual one, like Z and Z bar, and just take scalar product of corresponding vectors. This is what people study, and this is a statistical sum of corresponding conformal field theory. So if you have conformal field theory, that's how people started it. It is some kind of black box. In entrance, you have conformal field theory, and as in a box, it is some kind of work, and result is function on some data. it can be space of, no, in some cases it's space of matrix, and here it is space of complex structure, or complex structure is two complex structure, or complex structure and manifold M3. So this is what kind of this construction is gives us. Yes. So I explained this, and as usual, it is too long, but let me say only few words that what kind of generalization I have in mind. Suppose we have my construction working by the following. I have this point, and in each point I can say put some algebra. Yes, and then in principle I can make up all these things and find out this. One element of story is what? Suppose this algebra A depending in P. No, it is surely depending in P. We can put it in any points. Suppose on this AP we have a group of symmetries. Where G is, it can be Lie group or it can be discrete group, but this is group of symmetry in this algebra. So if you look carefully what is going on, in this case, this space VE, depending surely from complex structure, as I said, but additionally, it depends on a choice of flat connection on E. So generalization which we get by this way, now VE depends on complex structure and also representation of fundamental group of E to G. So in this case, the problem is that we can look what is happening if we change complex structure, and also what is happening if we deform the representation. And this is an interesting story. I cannot discuss it now, but such kind of data give you, first of all, this modular functor depending on representation, and second, if we make up all this, then dependence now not only complex structure, but also in representation of fundamental group and also connection. Now, in some sense, it is very similar, but it gives us, from the point of view of topology, new things. And no, I finish such story by the following, that there are two ways to think about this. What I said, that in a curve, in a point, we put theory with additional symmetry. No, this it was G, and if we use such kind of symmetry, we get, from topological point of view, new things. Or it is possible to say by the following way, that it is some conception of conformal algebras with big center. Very, very well known example is G hats, for example, SL2 hat, where my parameter k, which I did not explain what is this, equal critical, it is -2. In this case, such kind of algebra has a center, and this center are functions of authors. And authors are just differential operator of second order. Yes, and it has many applications, and in integrable system and other things, and in linked duality and so on. But it is big class of generalization of such kind of algebras, and so I'm talking about algebras A, which has something similar. It has commutative subalgebra, which are functions on some object like this. It can be connections, D plus A. Yes, and if we have such kind of structure, then and try to apply all business what I talked about, then the result of our construction depending on E and also choice of D plus A. And D plus A, it is connection on the curve, and it arises from the center. And time maybe is over, only last things which I want to say. That mathematically it is the following things which looks interesting. That from one part of a story, I have, so it is a way to make up the following. I have algebra A or conformal field theory where Lie group is acting. If you have this, you can construct the bigger algebra A tilde, where with big center, right? Commutative subalgebra is living, and this commutative subalgebra are a function on connections. Omega belong to G, so they are connection on the punctured disk. So omega is one form with value in G. So you can get such algebra, and after that you can recall all business about center on a critical level and try to do more or less the same, but with this different class of algebras. And you can do many things, and one, if I restrict myself only topological invariance, and topological invariance now depends on the choice of connection on three-dimensional manifold. But you can use it by many other things like center on the critical level, and it gives us so rather more algebraic. So anyway, so I want to say that no, it is going along the old line. So you have, for example, topological theory like conformal field theory, and it gives you something, some statistical sum. If you want more interesting things, you need theories with some additional structure. And as I said, such kind of structure can be different. Either it is action of a group, or it is big center which is living here. No, it is many. So by this way, we are always playing more or less by the same game, but conformal field theory is rather deep things. And so this set of new games appear rather often. So this is relatively new things, at least. Not so old as conformal field which itself, which exists 40 years, 50 years, and this is much, much younger. Not right now, but younger. Okay.
Questions?
So at the end here, you were saying if you have a conformal field theory with a symmetry,
Yes.
this group, you can construct a different algebra which has a large center.
Yes, yes.
How does the construction go, or is it complicated to explain?
No, it is. No, it is not very complicated. Up to something, you have algebra with G. Yes, and you have connection. Yes, if you have connection, you can look a little bit bigger. Manifold connection with solutions, choice of solution. Different way to use the solutions. It is up to action of a group. Therefore, manifold of connection with choice of solution, it is some kind of manifold where group is acting. After that, you have to take same direct product of this. So you take function on M times my algebra and take G invariance there. And it gives you the algebra with big center.
So
To do it honestly a little bit more complicated, but idea just this.
and is there a nice simple example like this SL2 hat? Can you take SL2 hat with SL2 acting?
Yes, you can. No, there are a lot of examples. Yes, and you can construct algebra with the action by many ways. Yes, and it is some kind of part of conformal fields series, which is because of some, it has a rather maybe non-correct name, logarithmic field series. And such kind of logarithmic field theory, it is just name for series with additional symmetries. In principle, logarithmic, it can be logarithmic or not in some sense, but it is named for that.
Well, I have one more question then. So earlier you were explaining how you could get this vector in the space of conformal blocks, either from the three manifold or from the complex structure.
Yes.
Is that related to this symmetries business or unrelated?
No, this is part of generic structure. It depends that if so, what is this? We have a Riemann surface and connection there. We can cook up vector space. And in this vector space, it is vector depending on complex structure, but it is some other vector depending on
Three manifold.
three manifold, but surely we have to extend connection to this manifold, and it depending on that. Yes.
Maybe one more announcement. So we will have a follow-up conference on Monday, on Thanksgiving Day. And the presentation, so Monday full day starting at 9 a.m. On the presentation theory.